And so we begin. Paul, it's your meeting. Welcome, everybody.
Okay, so do we have a time zone issue again? Is that the problem with people arriving?
I think so. I think when you change time zones, you might go plus, and we might go minus at just about the same time. So it's a
Right.
swing of 2 hours, which confuses everybody.
Yeah. Well, anyway, we'll proceed because it's being recorded and people can catch up. And I'm just going to take the screens in order on the Australian side. So, Andrew, you're the lucky first.
Thanks very much. And welcome everybody. Happy New Year. Happy New Year. So hopefully you can see a screen. So holiday time here means getting into radio astronomy. So I've been trying to work on a few different projects. I mentioned some time ago I was looking at an air gap patch feed for my little dish, and finally got around to making something. Thanks to Wolfgang Herrmann. I think some of Wolfgang's designs I noticed on the Sarah recording just recently, looking at the stacked disk Yagi and other things. So nice and compact here. I did test this with a nano VNA and got some good SWR, and I did put my Sawbird amplifier on it and did a bird bath check. Haven't seen much in the way of hydrogen yet, but you know how these things are. Small steps, and you don't get instant results in radio astronomy. So that's one of the things I'll be working on over the next few weeks. So hoping to get into a bit of drift scan hydrogen Doppler. This is just a bit of scrap aluminium I had, and it's mounted on the offset feed there, and just showing you just what it looks like. And that's just to remind you where I am. I'm down here in Tasmania off the southern end of Australia. So it's pretty dry down here at the moment. Next slide. The other little project I been meaning to get onto is some proper calibration of my systems. And I've been reading the Jove Cal 1 calibrator manual and started to order some bits and pieces. So thanks to Richard Flagg and James Brown and Jim Sky, nice little manual here. It's a neat little unit with a noise source and a programmable attenuator, and I'm hoping to use that to calibrate my systems. That's another project that will probably end up moving into our autumn. And I blew a bit of my hobby budget on some bits for a new antenna system. This is similar to the one that the South Australian folks have running for their Callisto. I bought myself the front end electronics for an LWA type antenna and a quadrature power coupler, and hopefully they're not far away in the post. And I'm hoping to set that up also in my yard and try and do some polarization measurements on Jupiter and the Sun and other things. So that's another one. So yeah, I've got plenty of activity happening at the moment. Sun's been quite active, so I did get a bit diverted by some solar activity, and there was a pretty interesting flare right at the end of last year, UT, early on the 1st of January for us here in Australia. The largest solar flare for a number of years, and produced some pretty spectacular and strong emissions. Here's a composite of some Owens Valley Radio Observatory long wave antenna data with my data in the middle here. I'm measuring from, in this case, 17 to 25 megahertz with a radio Jove type system that's using my loop antenna. And Stereo A, which is out not too far away from the Earth, but measuring things in the solar wind that are cut off by the Earth's ionosphere. So a nice sort of correspondence here. And there was some quite interesting fine structure in the latter part of this emission. And I did see a few folks in the Radio Jove and Ham Sci world had been looking at this event and looking at trying to publish something on that, which is great. And I've been having a bit of a look at some of the fine structure. I did make contact with sort of a fellow Tasmanian up north in our state who's also got a Radio Jove system and made some nice measurements as well. And anyway, so I started to have a look at this, and made some measurements of some nice small scale features. This is about 3 megahertz of bandwidth here over a few seconds, really. It's about 15 seconds across the bottom of each of these plots here, and 3 megahertz. So some quite fine structure, and these are quite interesting because these are subbursts in what's called type 2 herringbone structure. And if you look at the literature, there's not much on it. So I kind of got a bit busy and wrote a small paper on this, and I'm just about to submit that, and ended up look at some of the characteristics of the stuff. And if you, as I say, if you look in the literature, there's not much about these sort of bursts. And I built myself a little burst analyzer in software where I can pick out the fringes. And this is just showing some progression through the software where I have to contrast enhance, build with smoothing, and then I use some blob analysis, which David Fanning at Coyote software had developed, and modified that a bit, and ended up isolating these things, fitting some ellipses to them and getting some bandwidths and durations and the like. So that's been quite interesting. Sort of stuff you can do as an amateur, although I guess I've got the advantage of a few years of research behind me. But there's lots and lots of tools online now to do all sorts of nice image processing and AI tools as well to help you. So anybody's interested in blob analysis, I've got a bit of experience there. And then finally, there was another interesting flare the other day, actually a series of flares and also producing some fine scale structure again. This is 16 to 24 megahertz. So I went back to like a Radio Jove kind of setup, and some fairly slow drifting features here, bit like type 3B, if folks know about type 3B bursts. Some other little interesting things in here, these little fellas, sort of drift pair type bursts and type 1 and all sorts of other things in there. Some fringing down here, which is probably Faraday rotation in the Earth's ionosphere. So all sorts of sort of interesting things. Luckily, local interference at the time was fairly minimal. I've been having some trouble with some power inverters nearby, producing all sorts of garbage. But the interesting thing for me in here was I have another spectrograph running at 39 megahertz over about a 1.5 meg bandwidth, and seeing some what I think are S-bursts, which are sort of hard to see. These are really brief. They're the briefest type of solar burst. And I'm just seeing if my system can actually detect these. So again, small steps, you know, try and find these things. You might see them and then you keep improving until you actually really do see them. But these S-bursts are generally only 1 or 2 megahertz in frequency range, and literally maybe tens to hundreds of milliseconds in duration. So might even not even be able to see these on the screen, but they're pretty weak, plus some other things in there. So having a bit of fun looking at some of those things. That's me.
Thank you, Andrew. Amazing stuff. I think we're going to have to start selling tickets to visitors so visitors can come to your observatory and have a look around. It's certainly on my list to get down to Tasmania and call in one day and see what you're up to.
See all the spiders making nests on my antennas.
Yeah, I wonder where the name Cadiz comes from.
Well, actually, it's the old farm area here, which was subdivided many years ago, and it's the kind of road I'm on. So I thought I'll keep it the Cades, which is kind of it's an old Scottish word that means kind of a high point. But I'm down the valley a little bit. Yeah, trying to keep out of radio interference, but now it's creeping up the valley.
So it's Cades.
Yep.
Yep, very good. Any questions for Andrew from around the world? Some amazing stuff there. Andrew,
Okay. Yeah, I have
go
a
ahead,
question.
Preston. Yep.
I apologize. I had a phone call I had to take, so I went away for a few minutes. Andrew, were you talking earlier about a patch antenna?
Yeah, that's right. That's the air patch feed for my little dish for hydrogen line.
Okay.
Yep.
I noticed that one piece of metal, it was flat, but the corners were cut off. Is that
Yep.
part of the design?
Yeah, that's right. That allows you to measure circular polarization. Well, there are a few sources that are polarized. The sun can be. So I thought I might try and have a look at some, at least having it set up to be sensitive for circular polarization.
Thank you. That's
random.
Yeah, that's very interesting. Thank you.
Yeah, so very good. And Rich has put out a call for contributions to the next newsletter. Andrew, is there anything you can send over?
Yeah, should try and put a quick summary together of just the bits and pieces I've got.
In your spare time?
Yeah.
So is work getting in the way of some of this?
I'm on holiday at least until March now, so yeah, I should have some time. Although I do have another half that has some other ideas as well. So
Right. Yes. Great. Well, great stuff. Thank you, Andrew. And that's on the video. So going along my screen here, Steve, you're next.
Yes, good morning, everyone, and Happy New Year from Melbourne. And that was terrific, Andrew. Very impressive work you're doing there. I'm quite jealous. Our group, unfortunately, in the radio astronomy section of the ASV, are not as active as generating measurement reports. We've got a few systems that are down as well on our setup at Heathcote, and we're a little bit behind the eight ball in terms of preparing published reports of phenomena, and we completely missed the solar flare event, and we didn't make any records as far as I know. Anyway, I've been quite busy, as I always am, and as Paul knows. So I've got a few things to present. It's an update, first of all, on the development of the dish, the repair of our dish. So if you can bear with me, I'll put some issues up showing the progress of our repair of our big 8.5 meter fully rotatable dish. So I published this report on Christmas Eve last year, which is a potted history of the worn out worm drive gear for the elevation tilt adjustment of the dish. So it was worth putting this all together because it's quite a long and complicated story, and it took me several weeks to put it all together. So at least it's documented now, because this may be a legacy that we need to manage ongoing, because it could be a sign of weakness in the mechanical structure of our dish that we need to manage. So it's worth documenting it, because there wasn't very much about it. So basically, I've put this report together which describes, I'll zoom in a bit more, it describes where the worm gear is located. As you can see, it's a lot of force. This is a ton and a half or so of weight that's being tilted up and down by this jack screw going through that worm gear and driven by that gear motor and gearbox. And I found some technical information on the gearbox and technical information on the worm gear itself. So it does have a history of a commercial product, and that's what it sort of looks like. as an assembled unit taken out of the gearbox, because it's got these two end bearings as well that are added to the system, something that we might need to look at from time to time, the wear on those bearings as well. And if I can zoom in on the worn one, the worn out one, you can see evidence of what normally would have been a trapezoid thread. You can see where at one end it's starting to show signs of problems, but the other end was much worse. It's almost gone from a trapezoid to a triangular shape. So that was the evidence of the wear. And this is what we've done to redesign that gear. We've created these inserts that go inside the original gear, and we've made two of them. And I've actually got one, if you can look at my little insert on the camera, I've got one here in my hand. So that's a spare. And the other one is going into the telescope. So when that's assembled into the original ring gear using the Scotch key arrangement, this part is not under so much wear mechanically. It's bathed in grease inside a sealed gearbox, so that doesn't tend to wear much, and the load on it is pretty uniform throughout the whole operation. But it's the internal thread of the worm gear that wears out, so we've made that replaceable. The other thing that needed to be done was to have a big piece cut out of our tower so that we could fit bellows. And so that was an activity that was completed last year, as far as I recall. So you can see that's been done. And this is where we plan now to protect that exposed jack screw, which is very hardened steel jack screw, but it does get exposed to the weather, the rain, the dust and everything. And that's all going to get drawn down through that worm gear. So we're planning to fit bellows to the jack screw, and we've purchased a set of bellows, but you can see that there are 4 fixing points that we have to sort out. And so a recent exercise was to start measuring up in great detail all of these points where we've got to fix to. And that in itself raises a whole set of other mechanical problems to solve. So the first thing I've done in this draft report was at least document what we could in terms of the dimensions of the various fixing points. And in order to clear some of these structures, because they do go through a tilt arrangement, we're going to have to raise up the fitting to attach the bellows away from the structure so it doesn't strike anything. So there's the other fixing point, which is a lot easier to develop. That's at the bottom end of the jack screw. So I envisage like large 300mm size discs, which the bellows would attach to at each of these 4 points. And that's a diagram of the bellows, 230mm diameter. So that's why I say that they would attach to a 300mm disc, and we would perhaps use 2 half discs to sandwich the last spline of each end of the bellows. This is a bellows that was stretched out. So there's no issue really in stretching the length. We can get far more length out of it than we need, but it's the compression side of it that's really the problem. If I zoom into that, we did try to measure one. It's about 220 roughly as fully compressed, which is quite a big dynamic range of adjustment really. But we're not entirely sure whether that's yet enough, because it's a bit tricky to measure the actual clearances we've got. But this one at the top particularly is of concern to us, and it may not be quite enough. So that's an issue we're trying to look at the moment. The other end, the compression doesn't need to go anywhere near the 220. It's got quite a lot of space at the bottom end of the jack screw for compression. So we're starting to look at ways of now fixing this set of bellows, and that's the status we're at the moment. We've got a crew of people up at our property at Heathcote doing some work up there, and they're going to start doing some pencil designs of the bellows fittings, as well as do some repair on our property because we had some flooding rains go through there recently. I have another one to present. I've also been working on an antenna system up at Heathcote for neutral hydrogen. Because our big dish was out of action all of last year, I started looking at an alternative way of doing public demonstrations of neutral hydrogen. And our team built this horn antenna as one of our first experiments up at Heathcote, long before we had the dish in place. And you can see the dish in the background there, still with scaffold up against it for our repair work. So I started looking at getting this working, and I did some refurbishment of the receiver first of all. But then I couldn't get reliable performance of this horn to detect the neutral hydrogen. There was one occasion when I did. This was on a weekend before a star party at a public event. And I thought, great, we've got a winner. And then when the day came for the public event, it didn't work. I could not get any sign of the neutral hydrogen signature at all. Even when I pointed the horn at the sun, I got no additional signals coming out of the receiver. It was totally perplexing. I did a lot of fault finding and diagnostics of the cabling and power and everything. Couldn't find a fault. So there's a number of issues we still have to resolve with this thing. But one of the things I noticed first of all was our group had put a polycarbonate cover over the front, and that was covered in dust. And the clay dust up at Heathcote is notoriously metallic. You can put a magnet down on the ground and run it along the surface, and you'll pick up loads and loads of little bits of iron. So I'm not sure, but I think that's a feature that we're going to have to make removable. So that's one of the recommendations I've made for a future upgrade. The other thing that's interesting about our horn, it tapers down to a blunt end at this end, and I've taken the cover plate off at the end, and you can see our little monopole. And effectively, there was no waveguide. And so it was a bit of a checkered history on all of this. So I decided to delve into it and calculate how this horn actually works. So we've done a complete as-built measurement of the horn, and I've now documented that for the posterity, including the opening end there where the waveguide would have fitted, but we didn't fit a waveguide. I've done some calculations using various methods of doing it. There's a terrific online calculator that'll do it for you, and I can estimate what this horn that we've built will actually achieve. It's got a beam width of about 14 degrees, and I estimate the gain based on this calculator to be about 22.5 dBi. So it's quite a useful antenna if we could get it to work. But it wasn't built as you classically expect to see a horn. And here's an example I found on the web, and it's typical of most hobby horns. They're only about 1 metre long, these designs, but they do include a waveguide at the bottom. And I asked our team what was the basis of the way we built our horn, and one guy said, oh, we were using a scaled down version of the Ewan and Purcell classic historic horn, the original. And there's obviously you've seen photographs of this original horn for neutral hydrogen. And so that was a much larger structure. That's well documented how it works, and there's various web sources that provide details on that. And this is the actual dimensions of the Ewan and Purcell design. And based on the size of our horn that we built, I estimate that we've created a 3/4 scale version of the original. So that's something we can tell visitors and people at star parties and the general public, and educate them that we've created a 3/4 scale version of the original Ewan and Purcell horn. So why didn't we put a waveguide on the end? Well, that's a mystery lost in time. So I decided that the best thing we should do is to also incorporate the waveguide to feed the horn. So we've started out with the known cross sections, and I've provided some calculations that are fairly well understood by everybody, I think, of the cutoff frequency, just to determine that we can do this properly with the dimensions we have, and put the formulas in there. And I came up with the recommended dimensions for a proper waveguide. The position of the monopole element, we're going to make that adjustable, of course, so that you never know. There's always various functions that happen in any antenna you develop, particularly at these sub-microwave frequencies. You know, surface currents and so forth, they don't always work out as mathematically you determine. And particularly the monopole element, that sits in a socket, and the socket becomes part of the antenna as well. So you might think you've got to cut it at 52.8 millimeters, but it's usually something different. So all of those parameters will be adjustable to tune it to the right peak. So this is what I've recommended to the team that we proceed with. But unfortunately, when we put a waveguide at the end of that horn, we'll now have the feed point outside what was this toolbox arrangement, because the toolbox originally had a coupling straight into the element at the bottom of the waveguide, sorry, the horn. So we're going to have to put in a bit of small loss, unfortunately, to get that going. So that's yet another experiment that doesn't quite work, but I'm determined to make it work so that we have a backup system and also a demonstration system of a historic format of studying neutral hydrogen. It's also a wide beam width antenna. And I think that may prove to be useful in the future for actually collecting data and plotting it out. I've got a couple more things, Paul, if that's okay.
Yep, keep going.
All right. So there's another neutral hydrogen project we want to develop and install. We haven't installed it yet, but I've been restoring the elements of it because it had been in the weather at a different site down in Melbourne on a mountain called Mount Burnett. There's an observatory there which has a telescope, optical telescope, and it's quite frequented and supported by a local group of members. But they didn't show much interest in this interferometer they'd built. They had 2 parabolic dishes set up, and it's gone into decline. So they offered it to the ASV, and we've taken it on, and it's got a nice receiver, very well developed receiver. But I've started looking at the antenna system and found lots of deterioration, and I've begun restoring it. So I've restored the low noise amplifiers, and I've also restored the feed horns. They're very familiar devices, same as we use on our large dish as well. So we've now moved the dishes from their original home up at Mount Burnett up. They're now sitting on the ground at Heathcote, and you can see the struts there that hold the feed horn in place. So there's one dish on top of the other there sitting on the ground. But we didn't have any mechanical dimensions, and I couldn't find any other details on how this system worked at Mount Burnett. So what do? You measure everything up and you start quantifying it. So a recent exercise in December was to measure the diameter and so forth of the 2 parabolic dishes. And that way we can start working out the focal point and confirm that the feed horns are in the right focal point. Also work out some basic parameters using the available formulas. We think that parabolic dish should have a gain of about 28 dB. But then I began my very first foray into the whole study of feed horn fed parabolic dishes, and I had to learn about spillover and illumination taper and all of these familiar parameters that we're dealing with. I calculate the beam width of that dish is about 6.5 degrees as well. And the feed horn itself is another element to be analysed to determine if it's the correct size and shape and beam pattern. And so I did a bit of research on that, and I've documented that in this particular report. The structure of our feed horn is in this type of feed horn here with an F on D ratio of about 0.35. And that's the same that we're familiar with, a waveguide with a Kumar choke at the one end. So all of these things are starting to tell me that we've probably got an optimized system as it is, but I wanted to confirm that. I've analysed the feed horn mathematically as well. So that's got a gain of about 4.8 dBi with a beam width close to 100 degrees. But is that the correct beam width? So I started analysing all of these issues of spillover and illumination loss. And I may have interpreted this chart incorrectly, but I've done my best to determine the 3 dB points on these charts. This is a measured waveguide horn. A feed horn using a waveguide and a Kumar choke, and the dotted line was the horn on its own. The waveguide on its own, and the solid blue line was the waveguide with the Kumar choke on there. So this is off a web by this amateur radio operator who developed this system. So I've copied his diagram and done some detailed number grabbing off that chart. Anyway, what do we need for our parabolic dishes? I determined that from the trigonometry, we need twice 67 to get the beam width. But that's not strictly correct. That gives you 134 degrees, but that would create an illumination that has too much spillover. So what's the correct requirement? So I started looking into this whole science of spillover and illumination loss. And there's a chap, another radio amateur. I'll just zoom in on him there. This guy, Paul Wade, in 1994, he's published a report which I've pilfered and plagiarized a number of his charts. At least I gave him recognition there in the report. And he describes the required illumination pattern for a parabolic dish from a feed horn. And obviously there's an ideal desired pattern, which is the dotted line, but the solid line is the typical pattern you're going to get out of a feed horn. And so you under illuminate on those outer edges, and you have spillover loss where you're picking up, sending signal past the diameter of the dish. So there's a whole lot of studies that relate to this now, and this set of charts shows you what happens when you change the taper of the feed horn between 3 dB and 10 dB taper at the edges of the diameter of the dish. Also, what happens if you keep a particular taper, but then change the F/D ratio? So that's for different depths of dishes. There's a whole lot of examples there. So in conclusion, the optimum apparently is for an F/D ratio of 0.35, which is close to what we've got for that little interferometer system, has a taper of 10 dB. So you want the feed horn to taper about 10 dB down at the edge points of the beam width. And so I've summarized those results here. And based on that study, I conclude that the feed horn we've got illuminating that set of dishes we have for the interferometer are optimized. So we shouldn't have too many issues getting that system up and running. And at least now we know a little bit more detail about how it works. Thank you, Paul. That's enough from me. Oh, one more thing. Hope you can bear with me a little bit longer.
There's always one more.
I've got a terrific video to show, and I can't take credit for the development of this video. It was developed by Dr. Tim Davis, physicist, who previously worked for the CSIRO, and he modelled this. It's on the screen now. You're seeing the yellow background there. Good. So he modelled the proposed refurbished horn antenna, as I described. This is the as-built dimensions, correct ratio here, and the added waveguide to excite the horn. He modeled it using a simulation program, and it's absolutely a simulation. This is not a animation in this video that I'm about to play. It goes for a couple of minutes, 1.5 minutes. And every point on this field, the yellow field that you're seeing, is a high resolution calculation of Maxwell's equations. And so starting on the right-hand side, you'll see a wave come in. And this is the actual radio frequency electromagnetic wave shown in a slice in 2D, unfortunately. You're not seeing 3D. But you see the wave come in, and he slowed it down, so it's not happening at the speed of light, thank goodness. And over a period of 1.5 minutes, you see this wave travel down into the horn, and then you get the reflection pattern coming back off the end plate of the waveguide. And you see how the wave changes phase from the peaks and troughs and changes the pattern of the wave. And he's got a scale here of color with the magnitude of the amplitude of the wave oscillates between about plus or minus 3 at the peaks. So that's showing you'll get magnification of the wave by the effect of the horn. All right, let's run the video. It's very compelling to see the speed of light slowed down to these speeds and see how it interacts with the metal. So this is actually electromagnetic waves solving Maxwell's equations and how it interacts with the metal surface. There's even a little bit of calculation in there for the skin effect of the metal. And it's a really beautiful simulation that Dr. Tim Davis has created for us. He's currently over in Germany doing some research work for a German university. So the wave hasn't quite started reflecting back, but then it does. And as you start to see the reflection traveling back up through the horn, it takes a minute or so. Once you get to about the 1 minute point, the pattern starts to stabilize. And if we're going to fit our monopole element down here somewhere, that's where you want to see the peak, because that's the point where you're going to get maximum sensitivity. You don't want to put your monopole in a null of the waveform. It's interesting to see how the outside of the horn is also creating disturbance of the wave out in space. That's not something of interest to us at all. We want to know what's happening inside the horn. It's mesmerizing, isn't it?
It's very clever.
It's started to stabilize now. So that's the repetitive pattern from then on.
Yeah, red, blue, red, blue.
Yeah. So I think that's marvelous. And we've got certainly a terrific asset to our team in Dr. Tim Davis and his skills and his software development. And he did that simulation program for optics, but because it's Maxwell's equations, it's very translatable down to these radio frequencies we're using. And it's terrific to see this level of work. Thanks, gentlemen.
Great stuff. Thank you, Steve. And same question to you. Have you sent anything through to Russ yet? So to Rich for the newsletter?
I could package those 3 reports up if you like. I think it's worth, if they're certainly the development of, I spent quite a bit of time myself. It's a learning experience as much as anything to research some of the theory behind these things. So my level of understanding is a little bit below some of you guys, I'm sure. But at least I'm seeing it the best I can. And it's you don't get what you want from one source. I've noticed that. Even if you go to a textbook, 3 or 4 textbooks, you won't get what you want. If you go to a dozen websites, you won't get what you want. Andrew's nodding his head. So accumulation of any piece of research might be grabbing bits from everywhere to say the right story you want to tell. And for me, it takes hours, and sometimes it's 3 days, 3 solid days to put a report together. So I think it's worth publishing them, Paul. And even if there's some of it's known and understood, but it's my best effort at collating this information.
Yep, I think they're very valuable. That simulation, would Tim be happy for it to be circulated?
He certainly is. Yeah, look, he said to circulate it amongst the ASV, so it's public domain already, Paul. So we'll put it up for I'll post it off to Rich.
Yeah, that'd be good. I'm just thinking for my teaching, interference is part of the course at both International Baccalaureate and the local VCE, and that's a really good application of interference to the waves. I mean, you see the red, blue, red, blue, red, blue. Really, really good. Great teaching.
How waves reflect and then interfere with each other. Yeah,
Yep.
It's beautiful. It's a beautiful thing to see. And as Tim has often reminded us, what you're looking at there is not just an animation. Every pixel in that frame is a calculation on Maxwell's equations. That makes it even more compelling, doesn't it? Yeah.
I read a book about Maxwell and his work, and I'll try and find out the title. I've got it in one of my many piles of books here. And that itself is great stuff. Maxwell's equations. The fact that I think he got it down to 12, and then he kept working, got it down to 4 equations. Four is really good because you can fit them on a T-shirt. Maxwell's equations T-shirts. I mean, they are superb equations. They really are. And at the end of it, he said, "Well, electricity and magnetism propagate through free space at 3 times 10 to the 8 meters per second."
Yeah.
And other people said, "Oh, hang on a moment. That's the speed we've just discovered for the speed of light. Oh, I wonder whether light is electromagnetic radiation." So he came at it from the maths, and other people came at it from the practical experimental stuff, and they met in the middle.
Yep.
Absolutely superb science. Really, really good science.
Steve,
should
I'm
I
very
say
impressed with that
physics?
movie.
I'm sorry?
Thanks for the history. That's fun too. But Steve, I'm fascinated with the movie. Can you post the web address in the chat here? Thanks. If you
Well,
have.
it's a movie that I had on my computer here.
Oh, okay. It came from somewhere.
I can give it off to Rich. Is that the best way to do it, Paul?
What sort of size is it?
Oh, that's a good question. Just a moment. I'm preparing another report as we speak. Again, for our purposes up at Heathcote, we need a wideband receiving antenna, and I convinced the team to buy a disc cone, a VHF UHF disc cone. You must be familiar with them. They're an amateur radio product as much as anything. The video is 60 megabytes, so it'll have to be a link to a Dropbox or something like that.
Dropbox, yeah. The Dropbox should be good. If you or Tim can put it somewhere and then tell us where it is, that'd be really good.
Right.
I think it's a really good teaching tool. I mean, we could use it.
Slowing down the speed of light is brilliant to see as well.
Yeah, well, and we could use it on public open days to demonstrate what's actually happening inside the horn. Yeah, the idea that we're actually getting some amplification there. There's also another simulation which I've come across, which actually shows how slow the speed of light is. I'll see if I can find it while other people are talking. So it starts with light whizzing around the Earth, going in a circle, of course, which it wouldn't do, 7.5 times in a second. But then it goes out to the moon. So it shows a beam of light going back to, 2 seconds or something like that, Earth, Moon, Earth. Then it shows it going out to the planets and so on and so on. And what you see is this little dot of light creeping along very, very slowly, even on the scale of the solar system.
Yeah.
Never mind, once we leave the solar system and get out to in Proxima Centauri, 4 years, you're going to sit there for 4 years watching this dot of light on the screen.
Takes a lot of patience, Paul.
The speed of light is very slow, and that has massive implications, enormous implications. When we see these James Webb pictures coming back of the Pillars of Creation, which were just published recently, you're looking back billions of years in some of these pictures. Amazing stuff. I also feel like I've just wasted the last 2 months listening to what Andrew's been doing and what Steve's been doing. I've been sitting on a beach, reading a book, watching the seagulls walk by, and all those sorts of things. Do you want
to swap places, Paul?
That's I'm very happy doing the beach bit at this stage. All right, thank you, Andrew. Thank you, Steve. Next on my screen is Rob, and I saw Rob. You popped up in the Northern Hemisphere session recently as well. You must have got up very early in the morning.
I do that. I don't sleep all that much anymore. I'm assuming everyone can hear me. Happy New Year to Australia. Basically, what's happening is, I have a lot of construction here at the house, and basically what that means is the radio telescope's been pushed off into a corner, and nothing's barely been happening. But what I have done is I've made arrangements to go to Dallas, for the radio astronomy conference, and I've been asked to give a presentation about eclipses. And basically what I'm doing for that is resurrecting the presentation I gave in India a couple of years ago. So for me, I'm basically in the process of doing lots of things, but no results to show.
Very good. I'm never sure whether to include you on the Australian group or the American group. Rob, you seem to hop between the two.
I do that quite often.
Yep.
Keep me in both.
Okay, very good. Okay, moving through the screens. Duncan, you're next. What's happening in your area?
I'm doing a bit of work with the solar group, the Ecalisto, working on a noise source to try and calibrate the antenna. It's going quite well. Just injecting it in front of a Galley 74. So that's one little thing I'm doing. I'm going to share my screen. And I'm also timing the Vela pulsar off a 2.3 meter. And at the moment, I've only got one polarization up. So I'm on the stronger polarization of the Vela pulsar. So so you can, yeah, it's the Vela pulse period. So there's been a number of little glitches on the way with this one. You can see that sometimes the timing of the pulsar on the graph one is relatively noiseless. And then we've had a few other little timing issues, mainly understanding what was going on the Raspberry Pi. And so that's a trap set for the next glitch. The bottom left panel, graph 2, is the difference between a polynomial fit to the data. I'm looking for the difference, and the right-hand bottom panel is a pseudo flux density. It's basically SNR of plotted against MJD. So you can see there's a bit of variability. It's been a little bit wet in South Australia, so there's a bit of up and down in the signal to noise ratio. I suggest, yeah, and this is all, sorry, I should have backed up a bit and said this is all done at 820 megahertz, which may sound a little odd to people, but it's what I used to work in when I was doing this professionally. So I've continued on using the antenna that was developed for that, which is a chime-like antenna. I think I posted a 400 to 800 megahertz paper on sent it out on the SARA email. But this is a similar type antenna. This one's square and has dual polarization. Yeah, so I think that's about it to really say. There's lots of other little bits and pieces going on, but there's not. This is sort of the main scientific goal at the moment, to sit there and wait for the glitch. Does anybody have any questions?
Duncan, it's Andrew here. Nice job. Have you been in contact with anybody in Tasmania that might be of interest in your studies? The Tasmanian group does some timing of Vela still.
Yeah, I've forgotten the name of the gentleman down in Mount Pleasant. Yeah, I haven't been in touch with them recently. I usually get in touch when I think I've got there's a possibility of a glitch to actually get another station to get make sure there's a correlation between timing change. Yep, I'm well aware of them. Yep. Thank you.
Yep. Yeah, they're good. Yep, excellent. No, really good stuff.
So this is an old C-band dish. It's continuous. Oh no, maybe no. It's a 12 gig dish that had a unfortunate life, and a bit of panel beating has been done on it, and so it's not to be operated above 2 gigs. So I've just put it into action. In the next 6 months, the dish that's actually taking this data will actually go from being a transit instrument to being a tracking instrument, so I can keep an eye on it. So most of this is automatic. It's just have to run a terminal session on a host computer and set up, and it's just some software that runs it automatically, logs the data, and I just go in each morning after the 1 hour transit and reduce the data and get a number out. So that's about it from me.
My question, Duncan.
Yep.
So when we do see a glitch, how big will it appear on your charts there?
Well, that's a good question. It's a bit like measuring earthquakes. If it's a big glitch, I'll see it outside these errors. I've already seen one on a slightly bigger system. I think it was it was the last glitch that Steve Only, myself, and the Molonglo Radio Observatory saw. We'll just have to wait and see what the magnitude is. If it's a very big one, it'll stick out very clearly.
And a bit rusty in my knowledge of Euler, but 1 part in 10 to the 4 or something like that. So,
yeah,
something. Yeah, you should see it on that scale, I think.
Yep. And I think there's still some residual timing issues inside this. I've got a non-optimum site on the side of a building for the GPS antennas. So I think there's a problem with the number of satellites and getting a reasonable time. So that can, if that may inject some jitter into the timing systems. What I did discover though was going to a 64-bit operating system on the Raspberry Pi cleaned up a lot of the phase jumping that I was having in the data sets. Running over an hour, I might get 1 or 2 phase jumps, whereas where packets got dropped somewhere in the Raspberry Pi, and that seems to have been cured by somebody putting a circular buffer inside the Pi.
Is that a Pi 4 or a 5, Duncan?
It's a 4. There's 2 4s.
Okay.
This project's been in the background for I must have started it in 17 or 18. So yeah, it's just a small project going on. Anybody got any other questions? Sorry, I forgot to say the system temperature is about 100 Kelvin. I got a bit of spill, and quite a cold amplifier.
I'll just check my period change here. 3 by 10 to the -6 is the largest period change. So smaller than what I mentioned there by
tiny.
Yeah,
but I think you still see it from the.
I have a sort of general question. How come is it that all the neat stuff happens in the southern hemisphere?
I'm sorry that the center of the galaxy is down here.
Yeah.
Sorry, Don, you might have to move.
I might. I've considered. I've been to Oz a couple times, and it's been very instructive.
What I will say is my site, the level of interference in my site at present is actually decreasing, which is an interesting thing. It's mainly due for the migration from 3G to 4G mobile phones, so that's been useful.
Very good. Okay.
Hey, so just to break in for a moment here, I've actually got to go. We've got a show happening in town here. So my wife's behind me. I'm about to leave. So I really got nothing to report, and I'll probably see you next month.
Okay. Thanks, Roger. Thanks for coming in.
That's right. No worries. Thank you. It's been interesting.
Enjoy your show. All right. So, Duncan, my question as to the others is there something that you can send through to Rich for the newsletter? Or have you got anything documented?
I think
Go on, Duncan. Sorry.
I think I can document some of this. I also think I should document the change of the 2.3 to a tracking system.
Yep. So I should say welcome to Rich, and I think we've drummed up some reports for you, Rich, to go in your newsletter.
Excellent.
By the way, Paul, I've attached everything I presented this morning.
Yeah.
So that's on the chat. If anyone wants to download it, it seems like that 60 meg file, the video file, was uploaded okay. So you might get it downloaded quite quickly if you're good.
I asked to download it, and I think it came down. So I'll have a look. So, Rich, those reports are in the chat if you want them, or do you want them sent direct?
Also send them direct. That'd be great.
Yeah, I think then we know that they've gone through. Going to be a big newsletter. So I think that's everybody except me at this end, because Roger headed off. So I'll just quickly run through some of the things for me, and then Richard will be over to you for the US side of things, or to Ted, whoever's going to follow that through. Steve's mentioned our Heathcote dark sky site. That's been flooded for the second time. We had massive rains come through, very, very localized rains in some cases. So there were some rain bands go through and flooded, and it was all cleaned up. And now we have just had another set go through. So things are in a bit of a mess. Steve, have you been up? I haven't seen it.
No, I haven't been up there. Look, we've got these new walking tracks we put all over the property, and you could even roll a wheelchair over it. So we've made it all abilities access, as you know. And some of these asphalted trails go over little bridges, little culverts, where we've got a drainage trench that we put across the property, but they've blocked up when the floods came down, the drainage, and it's washed away some of the asphalt tracks. And yeah, there's a lot of mess. I think we're going to, I didn't go this weekend because it's too much physical labour for a guy in his late 60s. There's shovels and wheelbarrows, and they're moving all the muck that moved down to one end of the block. They're moving it back up to the other end with shovels. Plus, I think the main
that
club
cuts me out as well, then, Steve.
Yeah, that's right.
I'm even older. I'm even older than you are.
I think the main club room, which has got a concrete floor, that water went through there, so it's covered in mud as well. So there's a bit of mopping up. But look, it's nothing severe, and our dish is fine. It's sitting on a big concrete plinth, but some of the earthworks around it gets a bit eroded and looks messy. So it's a lot of it's cosmetic and for safety is the work that they're doing.
Yeah, it's worth mentioning. I think it's the town of Rochester, which is up that way, which got devastated. Was it last year or the year before? And it's just had it all again. So we're talking serious loss of loss of houses,
a foot deep water in your house. Yeah,
massive underwater. People have been living in caravans for 2 years and this sort of stuff. So it's all a bit of a mess. I think the stuff at Heathcote, yes, as you say, is cosmetic, and we'll deal with it. But at the same time, we need to think about those people who are displaced because of these floods and living in a caravan. It's not great. So that's that one. The next one from me is that there is this conference coming up. So late February, we have what's called a PhysCon conference, physics conference. This is for physics teachers, particularly in Victoria, although we do get some interstate people coming along. And last year I gave a paper on astronomy during the school day, all different ways in which we can do things which don't require dark skies and clear and whatever, starting with sundials and going all the way through. That included radio astronomy in its various forms, radio Jove, and so on. And so this year I'm going to do a paper on just that, on just radio astronomy, and how it links to the course at year 7 to year 10, which is determined by the Australian curriculum, and then the Victorian curriculum is the local interpretation of it. But also for year 11 and 12, our 2 last years of school, there's a lot of physics in that which can be demonstrated using radio astronomy. And that's why I'm interested in that simulation from Tim, because it's ideal. It's a lot of the course, as I go through, looking at the way that courses have been designated as part of the Australian curriculum and the Victorian curriculum, there's not a lot of doing science. It's learning about science rather than doing science. And it really, really needs addressing, because kids are sitting there in front of PowerPoints being told about what science is, instead of getting outside or on a lab bench or something, building things, playing with things. And as we all do, we try stuff, it doesn't work, we try something different. I can see Andrew nodding. I mean, you've been through the system as well. It really misses the point. It's made worse by the fact, I don't know what's happening in the States, but certainly here we are very short of teachers in general. We're particularly short of science teachers, and we're particularly short of physics teachers. So we have a lot of physics courses being taught by maths teachers, and that's fine, but their focus is the maths, not the physics. Yes, of course, maths is there as a tool. We see equations right through Steve's work, but there's an awful lot of descriptive work as well. We see a lot of year 7 to year 10 middle school science being taught by teachers who have never been taught any science. So what do? They grab a PowerPoint and they follow the PowerPoint, and it's boring as whatever you think, some rude word. It's an issue that really needs to be addressed. So part of my paper in late February will be about that. How do we get kids doing science? There is the Zooniverse. Some of you may be aware of Zooniverse, where that's citizen science. They're grabbing all this data from radio telescopes or whatever it is that they are. There's all sorts of projects. And kids can sit there and comb through this data and discover their own pulsar or their own whatever. So that's doing science in a sense. It's not hands-on. So I'm looking for ways of doing hands-on science. So that's what my paper is about. Once I get the PowerPoint organized, and yes, I will be using PowerPoint. It's efficient in lectures with adults. It's not efficient with kids. I'll give you an update next time we all get together. And the last one from me, I'm going to share a screen, is just a question or a sort of a, what do you think of this idea? I share that screen. Can you see a little box on a tripod? That is a robotic telescope. It's called the Sea Star. It's put out by ZWO, or for you guys, ZWO. It's an optical telescope. All right. So what has that got to do with our meeting here? Well, this is the question I'm raising. What has it got to do with our meeting here? This telescope is causing a lot of disruption. This and others like it. There are a number of different ones have come out, and you can see $900 Australian. They're about 500 US. It's a 25 millimeter lens on the front, and it's packed inside with ZWO electronics. So there's a Raspberry Pi in there. There's the ASI Air box, for those of you who are familiar with optical astronomy. It's like a guiding box. There's a dew heater for the lens, so if there's moisture in the air. And it's got a GPS. No, it uses the GPS in your phone. So it links to your phone initially by Bluetooth. Then you establish a Wi-Fi connection. Then you can connect it, if there's a local Wi-Fi available, you connect it to your home Wi-Fi. And you put the box outside, make sure it's level and the compass is calibrated. You go inside, pour yourself a glass of wine, and get onto your iPad, which is what I was doing last night, and produce pictures. So if I then just get rid of that and go to this one. So for example, I don't know how well you can see that. Do I need to make it bigger? Yeah, there we are. So that's C94, which I forget its common name, but that's a 9-minute exposure with this box sitting outside last night. This is a picture of Jupiter. Can I expand? How do I make it bigger? Full screen. No. You can see the shape itself, and this is Jupiter in the middle.
Maybe
And
Control plus on your keyboard.
Yeah, I just can't see a. Right, Control plus. I'll give it a go. No, it's not going to go. For some reason, I don't seem to be able to zoom in. I'll play around while other people are talking. But that's resolution enough to be able to see the bands on Jupiter. And people are getting to using this equipment now, this 500 US piece of kit. They're getting the bands actually showing the great red spot as well.
Paul, I think, did you demonstrate this also photographing the sun?
That's where I'm coming to. Yep. So you can see my pictures over this side. Here's another one. I don't know, that's C94. This one, which won't show very well, this Jupiter, but you can see the moons, 4 Galilean moons. This is last night. This is the moon last night. So full moon. And what people are doing is then stacking beyond that. And what's possibly relevant to us is this one, which is the live image of the sun. This is a picture I took, but I can have it sitting there live. And as far as we're concerned for radio astronomy, then we can keep an eye on, all right, what's the activity at the moment? The activity is quite low compared with what it was, say, a week or two ago, where it was really jumping. There were spots all over the sun. So my question, really, let me stop the share.
I wonder how they do that, whether they automatically bring a sun filter into the system or not.
There's the filter. I can go and grab it in a moment. It's just a little push-on friction fit.
Okay, you add it. Okay.
Yeah. So you open it up, you put the filter on, and then you say go to the sun, and it finds the sun. You see the sun whiz by as it overshoots, and then it comes back and sort of lines it up on your screen. It's got autofocus, and as
It's
I
only
say,
about say big, isn't it? The whole thing.
yeah, I'll go and grab it in a moment and wave it around in front of the camera. But it's a tiny little thing.
Beautiful.
But really, I guess what I'm saying. Well, two things. One is you could actually see the sun live. So if you're doing some radio astronomy which involves the sun, and you're interested in what's coming out of the sun at the moment, that's going to give you a very, very accurate, up-to-date view of what's going on. I know you can get it through the NASA SOHO site, but it's more fun to do it yourself. But the other thing is the disruption that this optical telescope is causing. The people who have paid $5,000 and $10,000 for high-end stuff are saying, "Oh, it's just a toy. It's just a toy." Well, it's not a toy. It's an entry level, and for me, I'm not prepared to go and spend $5,000 on gear. 10,000. My son does. My younger son has got a $5,000 set of equipment. It takes him about an hour to set it up. This takes 5 minutes. So you go outside. Oh, sky's clear. Put it out. Fire it up. Go inside. Where you go, you're getting results, and it's really disruptive. It's disruptive technology. It's upsetting a lot of people who have shelled out bucket loads of cash. My general question to this group then is there a point in the future where something similar could be happening for radio frequencies? So, and sort of a turn on and point type radio telescope that would just, it's outside, you're inside, and you'll measuring whatever you want to measure. I know we're talking a very different scale of things, but I just put that there as a question for people to think about.
I think the question is, it's just a sensor. What are you doing with the sensor is what is the real question. My concern is the level of abstraction that's becoming into society. And that means you can pick up your iPad and do something, but actually you don't understand how you got there. And it's through the levels of abstraction. Like, I think everybody on these screens can go from the very base level mostly right through to the highest level of abstraction today. People who haven't come through our pathways have a machine dumped on their laps. And I think, they can only go forward in the sensing sense, rather than understanding what actually has gone on to make this happen.
So that's up to us then to get the context, whether, I mean, in my case, through schools, in the case of others, through public outreach, through Astronomical Society Victoria, or yours, Duncan, public outreach, explaining what's going on. That's why that little simulation is so good. It actually, you can look down inside the horn, but you can't see what's going on. But with Tim's simulation, you get a feeling for, well, yeah, this is what's going on. I think because it's entry level, it's got me doing astrophotography. Let's put it that way. It's got me doing astrophotography for an investment of $700 or $800. And it's opening up the possibilities.
But the scientist in me will ask one question: what are you doing with the pictures? What is your actual aim? If you're going to do science, if you're going to collect pretty pictures, that's fine. But what are you going to do? What science can you do with it? And I think that's the difference in investigation.
Little gadgets, Paul. We're at a disadvantage with wavelength too, aren't we?
That's the issue. Yes, you've got a very different.
Some of our studies go down to a few kilohertz electromagnetic.
Yep.
Very long wavelengths, sadly.
Yes. I think
radio astronomers have a very I'm not going to do amateur or professional, maybe less in the professional ranks, but in the amateur ranks, the breadth of understanding of concrete, steel, machines, how to control them, how to record very weak signals, and then make some sense out of these very weak signals is a much larger breadth of understanding than a lot of the actual professional astronomers have.
That telescope sort of fits in with the style today. It seems like the goal is the main point of achievement. And people have lost understanding that it's the path, it's the process, it's the learning that goes on to get there that is the most enjoyable, and you gain more from that. Whereas this grabbing the picture, you're done. It's just like another cell phone application. And I think people will get bored with it because it takes no effort.
Yeah, I think there's more to it. I mean, what it's doing is taking 10-second grabs. So it runs for 10 seconds, it stores it. It runs for 10 seconds, it stores it. And at the end, actually, as it's going, it auto stacks those images. So you actually see the picture developing in front of you. You start with just a blank bit of sky, and then over 5 minutes, 10 minutes, whatever you want, however patient you are, the picture starts to appear. Well, essentially, that's what we're doing in radio astronomy. We're taking a signal, we're recording it, and then we're averaging over a period of time and building up a picture, which in this case can be maybe a graph or something like that. There are very strong parallels, and as a teaching tool, I believe that these little gadgets have got some potential. But I'm raising it, to stir things up. And the answer might be no. Wavelength is wrong, as Steve says.
Oh, no, Paul, you've got a point. It is disruptive, and it's making optical astronomy and photography very convenient and accessible to everybody at a reasonable price. You're quite right that for public demonstrations, maybe of neutral hydrogen or any other wavelength, maybe looking at the sun other than optical, little portable receivers are possible. They are possible. And we've done that sort of thing at Star Lake, haven't we? With a small 1 meter horn.
Yep.
So
I might argue that you've already been through one of these things with the introduction of SDRs.
Yep. I think that's a step in that direction. And if you coupled it with Alex's umbrella antenna, you're looking at something which is very, very affordable to put together and gives you a start.
It's unlikely to see commercial operators develop a radio astronomy equivalent of what you've shown there, Paul. We would have to do it ourselves.
Yes. Oh, there's no commercial market. ZWO's done it because they know there's a market in it.
Yep.
And Hestio, Vespera are just putting one out because of the eclipse, two eclipses you're getting in the US, and that's one where you just put your phone into the gadget, and then it's basically lens on the front of your phone, and all the smarts are in the phone because they're there already.
Our club president, Mark, does a lot of astrophotography with the phone.
He does, yes,
Yep.
and gets extremely good results. Yeah.
Just a comment.
A question.
And Andrew first, I think. Yeah.
Yep, thanks. Yeah, a very interesting discussion there. Yes, I agree with a lot of the points there. Can it do detection of transients and or movement of small objects? I'm thinking of things like, transient optical events. They could be occultations, they could be meteors, they could be asteroids moving across the field. Does it do that kind of detection? Because that would be something relevant to at least part of our group. It's certainly the meteor side of things and maybe the optical transients, because if you're looking for fast radio bursts and the like, you might get involved in looking at some of these transients. So if it can do some automatic detection of that, that would be pretty nice.
Yeah. It certainly picks up the satellites and the meteors and so on, because quite often you see the line across the image.
Right. Okay. So maybe a meteor application is one of the things. Yeah. Look, I think I like disruptive technology. I'm one of these people that said, "Oh yes, I must buy myself a good telescope one day," and I keep waiting for things to either come down in price or increase in capability. But I've got a little telescope. I do lunar occultations, and I mean that kind of thing. Yeah, it's probably not that suitable for that because I use a little video camera, and you really do need quite a high frame rate for that. But one of the people at the Astronomical Society of Tasmania, that's Lisa Bromfield, she's got one of these. She's an expert astrophotographer. If you're interested in upskilling, she's wonderful. She's got some amazing images with that little sea star. So look her up online if you're interested.
What was the name again?
Lisa Bromfield.
Bromfield.
Yep, you can find her on YouTube, Instagram, Facebook, X, you name it, she's there.
Is it Blom, BLOM?
BROM.
Or BROM, Bromfield.
Yep.
Yep. And somebody else had a comment?
He's done some live stuff with that as well, like solar, etc. Yep.
Somebody else had a comment.
No. So Paul, I have a question.
Yeah, Rob.
You take your ZWO and you take it out to where you don't have internet access. What happens to that unit? It doesn't work.
It does. Yeah, it's got a built-in compass. It knows where it is. You can feed in put in your coordinates as long as you know where you are.
Right. But you do the plate solve and it needs internet. Wi-Fi access. ASIR requires Wi-Fi access for it to resolve the plates.
Well, people are doing it without, as far as I'm aware. So I'll good point, and I'll find out.
And it's only a 2-inch aperture.
Yep.
It's limited on what it can do.
It certainly is.
It
That's
won't see
that-
what James Webb sees, that's for sure.
It's not a James Webb, but it's
But the point is, like you said, you just set it down and push the button, and you sit back and you can do all kinds of cool things with it.
yeah, that's right. But I mean, I did it the other day. I were down in the country in Warrnambool, and kids from the house where we were staying came out, and we had a great time with it because they saw stuff they'd never seen before. So in terms of outreach and education, it's a very, very powerful tool. But I'm being disruptive. That's fine. Stir things up a bit.
It's much easier than the Skywatcher system.
I'm sure it is.
And the Skywatcher's a 5-inch.
Yeah. I mean, you can turn it on and it'll do stuff for you. For some people, that's their first step. They've never done that before. So, I mean, I teach astronomy at U3A, University of the Third Age. And I've had people after the first session who go outside and say, well, that's the Southern Cross. And these are people of our age who have never seen the Southern Cross because they've never looked up. So even if it gets people looking up or thinking about what's in the sky or thinking about what's happening around them, then it's a good thing.
I agree.
Thanks, Rob. Rich, or are you going to take over from your end for your American friends?
Well, sure. Yeah, I've got a friend who has one of those things and he loves it. And he's a astronomer with a 12-inch scope and he'd rather use this.
Yep.
So I think just once you know how to do it, you know the basics, like you guys were saying, then you use it because you know what's going on inside of it. So you don't care. You're not trying to learn how to do it. And it's so easy to do. Yep. Ted, did you want to go first? And thanks for I missed my own time zone shift here. So sorry about that. Ted, you got anything?
I don't really. Let's get a microphone nearby. That's a little bit better. Not really new. I'm just keep tinkering on Ezra. We're talking more about our telescopes maybe tracking something in the sky or looking at a small object. Wouldn't it be nice if Ezra can kind of zoom in on a certain part of the sky? I'm thinking. And I was also thinking, well, some of our telescopes are small enough we could put it on a mount made for a telescope and then have it track something on the sky. So instead of azimuth and elevation being the input values, we could tell these smart tripods, just follow this point on the sky in right ascension declination. And so if Ezra had a way simply to take that as an input too, that would be handy. For that point on the sky, what is the power level kind of thing. Anyway, those are the things I'm playing with and just tinkering away. Something else I put in Ezra was I was curious when a certain part of the sky would be available to me without the Earth in the way. When can I see it? And so part of Ezra now posted already is an easy when, which will tell you for that object what hours of the UTC day it's above your horizon. Anyway, ideas like that. Of course, all that's in stellarium, but this might be a smaller thing to carry around. Mm-hmm. It gets straight to the point instead of clicking around with a mouse. Thanks, folks. This was fascinating.
All right. Thanks, Ted. And, this thing reminds me of how we collect pulsars, and that you're staring at one object for a long period of time and you're stacking it with a noise source, and the noise is averaging out and the actual signal is coming above the noise. So it works the same as the optical stacking when you go for a pulsar, but you're doing it with RF. So it's the exact same approach. And if we can take the pulsar software and go after some of these RF objects, then that might be the equivalent of this little box.
Yep.
Just one thing I'd like to see from an amateur point of view is amateurs participating in some of the big observatories, like having maybe a small antenna, but being an outsite, say for something like the long wavelength array. I guess you have to record stuff, at RF and then post-process it, but maybe there's a way of contributing there. We used to do that sort of thing with VLBI, you'd kind of record data and post it off and get it processed, but maybe that can happen even in real time. I know with things like, say, the radio sky spectrograph, you can actually share data online. So maybe there's a way of, using distributed antennas from amateurs to, do sky imaging at different wavelengths. Just an idea.
Yeah, and the other thing that I think RF people do that the opticals don't is that we rely on the shift from background to the actual total power signal going up when we cross the object. And so by staring at it and tracking it, you lose that differentiation about the, where the background low level is in the object. You've got a total power total. So it'd work with a spectrum, but probably not as much with total power if we track it, just like pulsars. I mean, that's where the pulsar stuff comes in, because it's pulsing and you can tell it's pulsing when you track it.
So one point there, Rich. So what you want really is a reference to compare to instead of quiet sky. And so you could look at a local resistor, for example.
Yeah, and the VLA and the ALMA, actually what they do is they look at it and then they go to a noise reference object, and they know exactly when they do that. So they can look at an object and track it, and then they shift off to a noise reference for a period of time, and then they go back. So we would have to do something like that where we constantly go to a reference signal, and then we can do a calibrated total power doing that method. And that would be something using tracking. We'd have to do something in that approach.
Yeah, it's a dicky
You're
switch.
doing it mechanically, and I was doing it electronically, maybe with a relay, but yeah.
Yeah, electronic. You have to have something. Yeah, you have to have something where you can shift it. That's like shifting to a noise source, a known noise source, and going back to the equivalent. I think. You're right, Ted. That worked too.
Yeah, that's a dicky switch. Yep. Zener diodes, very heavily padded, make good references as long as you can calibrate them.
My concern about a Dickey switch is I think it doesn't work as well for a range of frequencies. We're always interested in a spectrum of stuff. Did radar actually have a range of frequencies, or was it one CW signal?
Well, it depends what sort of radar system you're operating on, but they're usually fairly narrow band unless they're actually using noise radars, where they transmit noise and then use coherence to actually make a detection. The DSN use cal diodes. They switch between them to calibrate the system temperature for measuring, doing astronomy, and just to make sure the system's actually up on spec. Some of the diodes you can buy are, quite wide band, gigahertz.
I don't think I'm worried about the diode. The official Dickey switch used the resonance of a quarter wave coax, for example, so that they could compare to whatever was on the other end of that bridge. It was a fascinating circuit. Anyway, those are my thoughts there.
There are right now on eBay or Amazon, there are 0.1 dB single pole double throw switches with 0.1 dB insertion loss that are available for $3. And that's
Oh,
all,
yeah.
that's a price I'm interested in. Thank
yeah,
you.
that's all you really need for the front end Dickey switch, the Dickey switch receiver. They're broadband. You stick that right in the antenna feed. Don't put it on after the preamp like some people want to do, because that's not a real Dickey switch. Then you put one on the other end of the IF and Bob's your uncle. Feed it into a resistor capacitor, simple low pass filter, and stick an A to D converter on it, and you're done. And these days, with the RF chain being $30 or whatever the current price of an SDR is, you're essentially done. I mean, it's like their amplifiers are available. You could actually do it all at 1420, because there are dirt cheap amplifiers too. You can make an amplifier string to go behind your LNA and switch the whole thing at 1420 into a diode, a single diode detector, and a audio frequency sort of level low pass filter, and be done with. I've been wanting to try that. Maybe I'll get it done one of these days. If it ever gets above freezing here, we'll be in good shape.
One thing that calibration is, I think, one of the next steps, evolutions for our amateur groups. And one of the things that I attempted to do in the past, but I wasn't successful, is to calibrate the 10 centimeter solar observing. And what you do with that is you can actually relate that to the number of sunspots. That's correlated to sunspot, number of sunspots. And if we have but you need a calibrated Dickey switch at 10 centimeters in order to do the sunspot. And to do that, then you can correlate that to the number of sunspots using RF. And the NOAA site actually prints that. I forget what it's called. It's the
solar flux.
The solar flux number, right?
Yeah.
And but that's actually, if you plot them together, they're related to the number of sunspots. So you can do that. And I think that'd be a super project, and it gets us into calibration, and then we can go start correlating our results with the professional guys who are doing calibration on different total powers and stuff like that.
Well, they print the solar, or they publish the solar flux once a day. If you want the pretty raw data, you can go to the Penticton site of the Canadians. A guy now retired named Ken Tapping actually has a paper. We put it on, I think we put it in Sarah somewhere, Rich, on taking that, reducing that number and using it at other frequencies. It's reproducible. That's the point, and it's connected to a daily measurement of the solar flux. So you can point your telescope at the sun and record some data and do a calibration using that data directly.
Well, my ulterior motive is that the U.S. is using a Canadian telescope to get their data. And I think we ought to be able to take that job over. The U.S. ought to be able to get their own data instead of using the Canadian telescope. So that's my ulterior motive behind getting this solar flux stuff figured out on the U.S. side.
Well, it's true, but on the other hand, they maintain that setup very religiously. It's
I know that.
I visited up there, and they're very very careful with it. And you can depend on this calibration. I think that's where NOAA takes it. That's where NIST takes its solar information. I agree it would be fun to have an amateur approach. And I'm not really knocking it, Rich. I'm just saying that it's available if somebody wants to use it.
Don, I know you're closer to Canada than you are to the Colorado, so I understand your motivations with defending those guys. But all right, I'm just kidding here. Okay.
Me too.
Rich, can I just drag it back to the Dickey switch just for
go
a
for it.
second?
Yeah.
One of the things I have done in the past is with gas FETs where you have discretes is actually done what's called source coupling, where I've coupled a known diode noise source into the source lead of a gas FET, and then I've calibrated it that rise in system temperature on a noise figure meter, and that worked really well. We had about 352 amplifiers to keep eye on, and that allowed us to actually do the T-sys measurements and see what they were doing. Anyway, so there's other ways around it. Relays have mean time between failure on them, so a bit wary. If you do 100,000 cycles or something, you may if you're switching. Anyway, that's my thought.
Well, thanks. Let's see. Don, do you have anything else?
Nope, not at the moment. I think those little solid state switches ought to be. I don't know that I can invent and work with it right away, but I think that ought to be looked into as a Dickey receiver. And
okay,
there are other ways to even have more fun with Dickey receivers, because you can set that switch up in such a way as to be a null device, so that it's in a negative feedback loop, and you just record the value of the voltage you need to set the width of the noise pulse. Anyway, that's
well, it'd be nice if you guys could put together a 1 or 2 page thing on how to set one of these up on both the gas FETs and the switches. That'd be nice, because I think there's not enough knowledge in the Sarah group to and then we could hook one of these things up to the hydrogen detectors or the SDRs. That'd be the next evolution.
Yeah, my experience, I did try one of these experiments, and I was a little bit disappointed. The insertion loss of the solid state switches is quite high compared to what our noise temperatures, and you have to be careful, because the solid state switch insertion loss changes with frequency, and that's the relays actually you get a pretty flat response on the relays.
These the ones that I've looked at have a tenth of a they're quoting a tenth of a dB insertion loss. Now, whether that's real or not, I agree with you, Duncan. I agree that that's yet to be shown to be true. But if it is, that's a couple of a foot of coax or something like that. I don't know. It's countenanced because you're getting a 3 dB gain out of a Dickey switch. So I'm not sure.
Yeah. Okay. Well, let's shift on. We got a few more minutes here. Richard Flagg, do you got anything?
Can you hear me?
Yep.
All right. I got the microphone plugged in today for a change. I really don't have anything to add. It's been a fascinating discussion. The things that Andrew and Steve are doing are really interesting to me, and I look forward to reading some of that in more detail. And anyway, just a happy new year to everyone, and looking forward to the next meeting. Thanks so much.
Well, thanks. Alex.
Good evening. I don't have much more to add than what I did at the past presentations, but I'll, people that are present today haven't seen the videos from the past couple sessions. I'll show you just a 6-slide set of what's been going on. Been working on a circular patch feed. Just working. It always says too close to the edge. Is the screen up?
Looks great. But do stand close to your microphone. We're having internet problems.
Okay. I don't know if the internet may have cut off. Anyhow, had a few false starts. I've been basing the development on Dr. Vidmar's model and work that's over in Slovenia. Yeah. So the first one I built was a 1.5 meter long, 25 disc circular patch feed, and it works very well. And the thing that I was surprised and I don't understand is why it works so well, except for it's having a wider beam width, and that's still TBD. It's not all that different than this nice 0.27 F/D ratio parabolic reflector. I was very surprised that it performs so well. And this thing comes apart, splits in half, so it's portable. And I'm going to be hopefully running some tests tomorrow out in one of the local parks to try to do some better beam width measurements. This is the mini I've been working on. It's half the size. It's 30 inches long, 3/4 of a meter, and I'll show you how it compares to some of the other systems. It's not that bad, and it's relatively small. Tunes up nicely. I've been working on this, so I've gotten the tuning of this thing pretty much nailed. This is how a variety of these systems work. The top one is my 1.2 meter parabolic reflector, and it has a pretty good response. The next one down is the 1.5 meter circular patch feed, and it's pretty strong. And if you look at the T-SYS doing a comparison between Earth and sky, my parabolic is up at 7.2 dB. The 1.5 meters down to 5.9, and this little 3/4 meter is coming in here around about 5.8. I measured today about 5.5, but it's pretty strong. The umbrella antenna that Paul was referencing comes in at 4.2, and the unmodified, the Wi-Fi is pretty low because it has lots of spillover from its short 0.6 meter wide edges. I got some data from Jameson Adcock a couple days ago, and this is data from an unmodified scope in a box Wi-Fi dish. So these other systems are pretty good, and this is the one that I'm focusing on. I was thinking of trying to turn this into a kit, not having a lot of response. I thought I had a guy that was going to make these laser cut the discs, and I haven't had a response from him. But I've been working in the garage. Oh, this is what it looks like. It should have a fairly narrow beam. I measured this with a sun drift of having a full width half max of about 40 degrees. Not sure if that's valid or not. Hopefully be able to confirm that tomorrow, doing more of a range test. Where I spend the day or the week in the garage trying to figure out how to cut these discs in a more efficient way. That's the story.
Any questions for Alex?
One question is, mechanically, how do you turn that into two parts, that big long one?
This is a bit more sophisticated, and it doesn't have threaded rod. These are made out of aluminum tubes, 3/8 aluminum tubing. and I have sections that either screw together or telescope together. There's a lot of engineering that went in that. I would not want to manufacture them. That's a one of a kind, but it slides together and comes apart. There are steel reinforcements in there to keep it from bending at the joints. I enjoy doing mechanical work, trying to figure out how to do these things. So I put a lot of effort into the build-up project as well as.
Congratulations. That's a tricky question. Neatly done.
You have a lovely workshop there, Alex, too.
Oh yeah.
How much does it weigh roughly?
Well,
kilograms?
The short one, the heaviest part is the 10 millimeter, 3/8 inch stainless steel threaded backbone. Here, this is the short one. I don't know what it weighs. About a pound, maybe pound and a half. But it's
that's nothing.
No. I mean, and so it has the threaded rod as the backbone, and this one I have aluminum spacing. And you could build it with nuts, but this is a big deal. Every element in here. What I was surprised, this is a electromagnetically tuned system. I found that by shifting one of these things 5 millimeters gave me a better resonant frequency. So it's easier to put spacers in here to define the spacing, and I'd have this thing operational into the VNA and have the rod this loosened up a little bit, and I had some plastic device that I could separate these elements and shift them around and play with them. So the real answer doesn't match the model, but you can tweak it up and have it work pretty well. But the patch feed is one of the most critical to tune antenna elements that I have found. I mean, you're talking about sub-millimeter to really tweak it to 1420, but it's fun.
Brilliant. Thank you.
I wonder how much torque you could get out of your little 2-inch telescope drive. Find a way to counterweight that thing and piggyback it on that telescope drive, and your pointing system is done.
Well, I mean, I have this on. I bought a little Explore Scientific, their low-cost EQ3, and it fits fine on that. I mean, you can put this on an equatorial mount. And I mean, it really works nice on an equatorial mount because you set it up, you can use a digital level, and then if you want to move it a few hours before or a few hours after, you just use the RA scale and you know where you are. You bring up stellarium, say it should be here rotated over rather than having to deal with elevation and azimuth. So an equatorial mount for a backyard type setup is very effective.
Alex, that's really neat. It's a really nice unit there. Of course, you can use less elements and use it also as a feed for your dish too. I guess people will do that. Go watch spillover, of course, but if you have less elements, you get a wider beam, and you can use that also as a feed on a dish. But yeah, really nice. I think that's actually a really good example where, you know, this sort of thing could actually go out for schools and, you know, general public, and you could have a whole network of hydrogen line folks out there with a simple system.
Maybe work. Alex has invented the disruptor, Paul.
Yeah, I mean, that's what it looks like. It looks like some kind of a space weapon or something. You can, I mean, you have seen them on the internet with shorter ones. Ted has built them. They have a wider beam width. But what really amazed me was that it does not pick up a lot of ground noise. I was really surprised that it has such a dramatic cold sky to hot earth differential. It's not shielded like a parabola is from the Earth.
So there is a thought that that we could mass produce these discs and put them into kits. So that's sort of what Alex is sort of pursuing. If we can find someone to cut these discs out and then maybe put them in kits so we can sell from Sarah. So think of that. If you guys know anybody that could help produce this stuff, that might be what we'd want to do. And I think that would really jumpstart instead of people buying these dishes, and this would be more fun for them to put together and a lot.
What I was thinking is have all of the elements and spacers in the kit and just have them buy the stainless steel rod, because the rod is only $6. It would cost you that much in delivery fees to send it to somebody. So you could have all the elements in a small box. They buy the threaded rod off of Amazon and stack it.
Yeah, that's a great idea.
Yeah, I think it has that. The CNC manufacturer looks pretty good for that.
There was one guy on eBay that I exchanged an email. Initially, he told me he'd make the small discs, the directors, for $1 a piece, which seemed okay. I sent him a diagram describing the more complex ones that require holes, and haven't gotten a reply. I called a shop locally, and they wanted $5 a disc. That's way off scale.
Okay. All right. And last but not least is Preston.
Well, I really don't have anything to add, but I would like to say that I thought the presentations tonight were really impressive, and I really enjoyed seeing them.
All right. Okay. Paul, that's all I think that's all of us. Do you got anything else?
No, we've been through our list. You can catch up on the video, and I think we've covered a lot of ground today. So very, very good.
Okay.
I've sent you an email, Rich, which contains my PDFs and a link to the video that I gave.
Excellent. Thank you.
All right. So see you in a month.
All right. See you, buddy.
Thank you.
See you later.